Okay, so I'm going to go into a bit more detail on some of the cosmology that we're now able to do by having probed the CMB to much higher angular resolution than we had just a few years ago, both from Planck, but also from the ground-based experiments. So if we're thinking about the small-scale CMB, and I'm kind of roughly going to talk about small-scale CMB as things smaller scale than WMAP, because that's what we had a few years ago, and now we've moved on from that. And so we're talking about scales sub a fifth of a degree or so in the sky. And we're measuring now the CMB to arc-minute resolution, or a few arc minutes. When we measure the CMB at high resolution, we're actually probing two epochs now. We're probing the redshift of 1,000 recombination epoch, and we're then looking at the usual acoustic oscillation physics, and we're looking at the silk damping that comes from the acoustic oscillations being washed out during the recombination process if they're very small scales. But now we're also looking at late time physics, because the CMB is gravitationally lensed, as George showed the data of from Planck. The CMB as a backlight gets distorted by all the large-scale structure in between us, and the signal gets coherently distorted. And that's picking up mainly signals that dominate at redshift about 1 to 3, but really you're picking up large-scale structure all the way from recombination to today. So you've got these two different measurements. So I'm going to talk about results from two experiments that I've been working on. One is the Atacama Cosmology Telescope, led by Lyman Page in Princeton. We're also going to talk by Renee Lojek this afternoon on that, as well as Planck, which we've already been hearing from George. Here's the slide of all the contributors. Okay, so we've now got this enormous dynamic range of scales that have been probed by the CMB. You've already seen the plot from Planck. This was our final power spectrum measured of the CMB by ACT earlier this year. As usual, I'm showing the power spectrum against multipole here, and now on a log scale, where the blue data points are WMAP, and the red data points are ACT. And it's going all the way from L of 500 actually out to, we're seeing the CMB, or can extract the CMB out to almost L of 4,000, which is actually well beyond where Planck can go. So Planck is going out to about 2,500 here. As George mentioned earlier, this spectrum is the CMB itself, with any extra foregrounds and nuisance parameters already marginalized over, removed, and with their uncertainties propagated into those errors. So what you're seeing there is just the CMB. But the only way we can get that is by measuring the CMB all the way out to even small angular scales, and fitting for extragalactic foregrounds, fitting for effects from clusters, from point sources. But I have great confidence that we've been able to do that. We've done a huge amount of tests of different models. You do that, you fit them, you remove them, and what you get back is just the primary lensed CMB. And so we're seeing now 9 acoustic peaks in the power spectrum, and beautifully we're seeing the silk damping, where what we see is just bang on with lambda CDM, and that's what George already mentioned, that what we're not seeing is power that's coming up here or down here or wiggling in a different way than we'd expect from lambda CDM. It's really bang on. So we can then look at the current sort of compilation of all the small scale measurements, including Planck as well. And Planck then beautifully gets the L of less than 2,500 range that George already showed. This again is now on the log scale up here. And in red is Planck. The blue points I just showed you from ACT are underneath and very consistent. And in yellow are measurements from the South Pole Telescope, which has also been measuring the sky at small scales. So we're seeing right out to L of 3,000 and beyond in the CMB. There's really great consistency between these data sets. Planck is fantastic, but we've used, for doing Planck analysis, we have, as George said, used information from ACT and SPT. And even before Planck, we were seeing these small-scale features from ACT. I just want to show you quickly and go back to the previous slide that it's not enough just to say that the power spectra agree. We've got these different observations now of the high-resolution CMB that are incredibly consistent. And this is showing you just new results of the cross-correlation between the region of sky observed by the Atacama Cosmology telescope, which is roughly 600 square degrees, cross-correlated with the same overlapping region of the sky seen by Planck, because we want to see if we're seeing the same signal. And we are. What I'm showing you here is the power spectrum in the range L of 500 to 2000 of the ACT power spectrum and the cross-correlation between ACT and Planck. And they're incredibly consistent and agree really very well. And that's saying we are seeing the same sky by these different experiments. So with these small-scale features, we can now ask a number of questions. We can probe inflation, test inflationary models. We can ask about dark energy, whether we have any evidence for a dynamical component in it. We can ask about what are the masses of the neutrinos. We can also question, are there additional relativistic species that we can see in the universe? Or are there actually other high energy signatures that we can see? Because by having all of these features in the power spectrum, going from 3 acoustic peaks to 9 is helping us a huge amount. So let me just show you a few examples of how measuring those small scales can help us test early universe physics. Now, I know that the main result is we don't see any new evidence of physics, but that just means that we have to try a bit harder. We heard yesterday that Susie hasn't been seen yet at LHC. You don't stop looking. There's so many things we don't understand in cosmology that we just need to now keep looking and looking harder and harder for signatures of physics that could explain some of our outstanding questions. Okay, so what can you do? How can you do? What things can you probe by measuring more acoustic peaks and smaller scales? The first thing is you're testing recombination, and you can test things that affect the contents of the universe. We usually assume just our simple lambda CDM model, but you can change the contents of the universe. You can put in different numbers of neutrinos, different amounts of helium. You can put in a modified dark energy model that, for example, has early dark energy, a fraction of dark energy at early times. You can also put in additional physics, like a dark matter component that annihilates and affects the recombination process by adding in extra sources, by changing the ionization fraction of the universe during recombination. Or you can vary the constants of nature and say that that's going to vary too. Those things will all affect the acoustic oscillations and the silk damping process during recombination. So you can test those. The second kind of class of things you can test is by extending the angular range that you see the CMB over. You can just simply probe the primordial power spectrum over more decades of scale. And that will tell you things about the spectral index and the running of the index, the scale dependence of the spectral index. And by going to these small scales too, you can also probe scales where non-standard fluctuations might show up. So usually we assume that fluctuations are adiabatic, but you could also have isocurvature contributions. You could also have contributions from cosmic strings, for example. And these will show up at small scales. And then below that, what I'm showing you is an illustration of 3 examples of that. This power spectrum has been scaled by L squared to bring out the higher acoustic peaks. And here it's now ranging out to L of 3,000 or so. So this L to the 4, so this is now an L to the 4 CL plot, where these 3 first acoustic peaks are the ones probed by WMAP. And then these higher acoustic peaks are the ones probed. And on here, I'm showing the ACT results. But then Planck now nicely covers the ranges out to here. Lambda CDM is shown in the dashed curve, together with 3 models that are essentially indistinguishable at these larger scales, L less than 1,000, but show up quite dramatically differently at small scales. The first one has a strong negative running of the spectral index, a strong scale dependence that we wouldn't expect from simple inflation. And if you have that, then you can fit the data or agree with the data at large scales, but then you'll increasingly damp your spectrum at small scales because your primordial fluctuations are just dying off if you've got a strong negative running. The next model has 10 neutrino species rather than just the usual 3. That also affects the spectrum, and I'll say a bit more about that in the next slide. We also have a universe which has double the amount of helium that we expect from standard BBN. Again, that damps the spectrum, and we see it looking completely different to the one probed by the data. So this information can be used to really significantly improve constraints, even if we're not seeing signatures of new physics yet. So let me just go into a bit more detail on those. Primordial helium, again, we usually assume that BBN is right. And as soon as you know the baryon density in the universe and the number of neutrino species, you can say exactly what the helium fraction should be. And so we usually fix it at 0.24, 0.25. But we can vary it and use it to test BBN instead. And this shows the power of using the small scale data, because this is the distribution of the helium fraction measured, first of all, using just the doubly mapped data. You can see it's very broad and includes this point at 0.5, double the helium fraction we'd expect. It's not excluded by the data. But as soon as we add the small scales from ACT, that shrinks down significantly and goes towards something that looks in pretty good agreement with what we would expect from BBN. That shrunk even further with Planck. And over here, so I'm showing you the constraints on the helium fraction against baryon density from Planck, combined with the high L experiments too. And we're now getting a helium measurement that's 2%. And it's becoming comparable to that band. This is the band of direct measurements of the helium fraction from BBN itself. That's looking rather consistent. This is only going to improve. So the reason we can see it so well is that it's very, you increase the helium, you decrease the electron density, and you just increase the mean free path of photons during recombination and increase the silk damping. So it's a very simple effect on the spectrum. And having polarization as well, where you're also measuring the damping scale, will help that too. So this is something that will continue to be better measured from the CMB. But as yet, that looks consistent with BBN. Relativistic species, this is something that's been of a lot of interest in the last few years because earlier measurements from small-scale experiments were hinting at the fact that there might be more than 3 species in the universe. So what we usually do in cosmology is we assume 3 neutrino species, but we can vary the amount of relativistic density. And we do it by, we don't say it's neutrinos, we just say I'm allowed to tune the knob that tunes the amount of relativistic density in the universe, stuff that doesn't couple to baryons. It doesn't have to be neutrinos. And in our analysis, we're not assuming it is neutrinos, but we then usually call it an effective number of species as something that looks like neutrinos. If you boost up the amount of relativistic stuff, you have a longer radiation domination period, which shifts the acoustic peaks. You also suppress the acoustic oscillations because you've got stuff that's now not coupled to the baryons. And you also add a small phase shift in the CMB at small scales because you've got perturbations that are propagating at the speed of light rather than the speed of sound in your cosmic fluid. And all that means that it shows up quite significantly different at small scales. And again, this is a plot from the final ACT analysis showing how much you then reduce the distribution from doubly map down to one from the combination with doubly map and ACT that's much more tightly constrained. And from ACT and doubly map came out to be just under 3 plus or minus 0.5. And combined with SPT as well, just over 3 plus or minus 0.4. And then with Planck, we get a very consistent number of just over 3 with an error bar that's 1 sigma away from 3. So this has been a really strong improvement in just the last few years. And if we look at it on the plane of the number of species against the baryon density, this is the Planck constraint here. And these are the primordial BBN, or the BBN measurements of helium and deuterium from direct measurements. And so now our constraints from the CMB are tighter than the ones from BBN measurements. Now, that number is consistent with 3, but there's still a little bit of wiggle room for it to be a little bit higher than 3, and I know that's a lot of interest. I think we're going to hear from Joe Conlon on Thursday about whether that could be a signature of axion physics or other new components that could add even just a fraction of a neutrino species. So this is somewhere we're going to have incredible improvement in the next few years. We've already had incredible improvements, but we can shrink that even further, again, with polarization measurements of the CMB. We're aiming at going down to error bars of 0.1 and then below from future CMB measurements. And so if that number really is 3.3 or 3.1, we'll start to get a hint of that. But so far, it's highly consistent with no extra species. So those are kind of additional components that we could have in the universe. The primordial spectrum, I've said we have now this twice the angular range we had before, and that allows us to probe the primordial spectrum a lot better. One expects from simple single field inflation to have a few predictions, that the spectral index should be less than 1, and that the running of the spectral index should be very small, 10 to the minus 3 or less. Again, from measuring those smaller scales, we can exclude more negative runnings of the spectral index that used to be allowed. First of all, I'm showing you the results from WMAP and ACT on the spectral index and the running, where this used to be the allowed region with quite a negative running allowed, and that's now shrunk down significantly to having only a running of about 1% allowed from the CMB. But the other big thing that George mentioned as well is that then when you switch to having Planck, this is the Planck result over here. I'm afraid now twisted by the axes are now flipped. The running is still very consistent with 0 to 1 sigma, but now the index is measured to be less than 1 at very high significance. And that's a result that's strongly present in the Planck data. So we're getting down to 1% errors on the running. There is this slight preference for a negative running, but it's at the 1 sigma level. And I wouldn't say that was suggestive of new physics. Where we'd really like to get to is the running of the index that one would actually expect from inflation. But that's kind of beyond the scope of the CMB, although it shouldn't be necessarily beyond the scope of combined large-scale structure measurements, perhaps in 21 centimeter. There have been papers on how to get down to the level that we'd actually expect from inflation. Okay, and the last example I want to give from the primordial CMB are cosmic strings. So I said that one of the things that you can probe at small scales is fluctuations beyond just adiabatic fluctuations. This is a bit of a busy plot, I realize, but I just want to remind people how that's done. So how we constrain, we know that cosmic strings cannot be the primary source of fluctuations. They have completely the wrong power spectrum now measured from the CMB. But they do add, you could have a subdominant component of them, and one can predict what that should look like with simulations. Now, the simulations are quite uncertain, but they at least give us a good sense of what the additional power could look like. So what I'm showing you here is again, an L to the 4th tipped up power spectrums to enhance the higher acoustic peaks. The magenta curve is the sort of standard adiabatic normal fluctuations. And down here would be the additional power that one would expect from cosmic strings. And so how we do it is we simply can scale that additional power by a cosmic string tension and add it to the adiabatic fluctuations and see what you can have. And so, as you can imagine, by having new constraints at small scales, L of 2,000 to 3,000, where this string spectrum is still non-negligible, but the inflationary one is dying off, or the adiabatic one is dying off, the total in blue will start to exceed or start to be inconsistent with the data. And that's what's given us now this current, the data on this plot is old, but with the current data, the string constraints are on at least one type of string model, Nambu string simulations from Richard Batty, are less than 10 to the minus 7 in the string tension. And when you include that, we still find that, we now find that the spectral index of fluctuations is still less than 1, even if you allow the cosmic string tension to vary. And that didn't used to be the case. There used to be this case where you could have some cosmic strings and a spectral index of 1. And that could be consistent with hybrid inflation or models like that. That's gone now because you still, the spectral index is now preferred to be less than 1. Okay, so we're not seeing anything new, but we're constraining things a huge amount better than before. And I haven't gone through the other extensions to Lambda CDM. They're all tighter, and we're not seeing any new physics. But these are also all things that will improve with polarization data. Okay, so I want to then move on to what we're learning from lensing of the CMB. So as I said earlier, you've got lensing. The background CMB is lensed by large-scale structure. And this is a cartoon, very cartoon diagram of how a CMB photon can be gravitationally deflected by a large-scale structure and hit us now. And we'll measure it. We'll measure the lensed temperature as being the unlensed temperature plus a deflection field. So every single photon that's coming to us is deflected by a very small amount due to large-scale structure. The deflection angle is of order a couple of arc minutes. And that explains why this is something that's now new and coming from small-scale CMB measurements. You just couldn't see it if you didn't have small-scale measurements. We can write down, so imagine you've got the CMB as a backlight, and you've now got everywhere on the sky a deflection field that you can think of as, so we'll write it down normally either as a deflection angle, so every pixel in the sky has an angle, or you can write down the angle as the gradient of some deflection field phi. So you have a field phi on the sky that says what your deflection is. Theoretically, that power spectrum, the power spectrum of the deflection angles, the two-point function of the deflection angle, is just the line of sight integral of a geometric term scaling the dark matter power spectrum. This is just simple lensing physics, that your CMB light is just gravitationally bent by every blob of dark matter or normal matter along its line of sight. So the physics of that is nice and simple. And crucially, you don't have any kind of bias terms in here because we're just talking about matter. We don't care what kind of matter it is. So the effect is small. You can't see it very well by eye. So here's a plot from Aurélien Benoit-Levy on showing the lensed and unlensed CMB on a 2.5-degree patch of the sky. And you can't really see very well the difference. But if we then switch this one between being lensed and unlensed, you can see there is a shift. And what you're seeing is a very small shift, but a coherent shift, because the CMB is being deflected by coherent structures, because these are large-scale structures, degree scale in the sky. So this coherent shift means you can actually look for, you can then you can take these maps and unwrap them and figure out what was causing that deflection. That's what's been done. So this shows the compilation of the current CMB lensing measurements. The first measurement was by ACT in 2011, which was a 4 sigma measurement. And I'm showing you here just the updated measurement of that in red here. And so again, this is the two-point function of the lensing field against multipole L. We reconstruct that lensing field by taking higher point statistics of the map. Roughly, you'd get it by taking the temperature of the CMB map and the gradient of the temperature, and you find the 2-point function of that. So the lensing potential is actually a 4-point function, or the lensing potential power spectrum is a 4-point function. You can also see it in the power spectrum itself. It smears out the acoustic peaks. Lensing smears the peaks and adds small-scale power. But more information can be got if you can actually reconstruct the lensing potential itself. So the ACT data points are shown in red. Then this was followed by SPT, making a detection. These are shown in the yellow. And then the data points from Planck are shown here. So we went from 4 sigma to 25 sigma just in the last couple of years. So again, this is a fast-moving field. And as George already showed, these are consistent with the lambda CDM model that's shown on top of them. The neat thing, I think the neatest thing that we've been able to do first off with CMB lensing is to finally break the geometric degeneracy that's in the CMB internally. We've always had this case that you cannot distinguish, or you can't disentangle varying geometries from varying expansion rates of the universe in the CMB if you only have the primary signal. You can always come up with models that look the same. You can have a model with no dark energy that's strongly curved, and it looks the same as lambda CDM in the primary CMB. And so we've always had to combine the CMB with other measurements to detect dark energy, for example, and to constrain late-time physics. That's now been finally broken just internally to the CMB, and you can see why here. So up here, I'm showing you a plot of the deflection power spectrum. These are theory curves. The deflection power spectrum is a function of angular scale. Here is the lambda CDM model in blue, and in green is a model that is degenerate in the primary CMB, but looks completely different in the lensing. This is a model with no dark energy that's geometrically curved, and it just has twice as much lensing because you've got large-scale structure at late times that increases the amount of lensing you see. We use that in ACT to break this degeneracy between omega lambda. So we've got omega lambda and omega matter here. Previously, this model down here with no dark energy was allowed by the CMB, and with ACT lensing, we cut that off and made a detection of dark energy. This is now already significantly improved by going in the lensing from a 4 sigma measurement to 25 sigma measurement with Planck. And so now here's where we are with Planck, same omega lambda, omega matter, where that black contour is what we now have from Planck, which is, highly, highly strongly saying we need dark energy. Now, you already get better, right now you get better information by adding the BAO measurements. And certainly, if you want to understand dark energy at late-time physics, you want to be combining measurements. But this just illustrates that the CMB lensing is already contributing significantly to understanding late-time physics. Okay, what's next? So at the moment, I would say that CMB lensing is improving constraints. So things like neutrino, we've heard that things like neutrino mass constraints are slightly improved or slightly modified with lensing. But it's not yet giving us new information about significant new physics information. But that's going to change in the next few years. I think so CMB lensing is really taking off. And how we're going to be doing that is through measuring small-scale polarization. I've talked completely just about temperature so far. But polarization is where things are going. We've already seen the results from George showing the Planck pre-polarization results. We're going to hear more from John about B modes. But what we're doing with small-scale polarization is going after a couple of things. This curve up here shows you the temperature power spectrum. But what we're going to be measuring with ACT-Pol, which is a new instrument, the upgrade to ACT, is the polarization power spectrum. And this is shown in green here, the E mode, and the cross correlation in red. In blue is the lensing power spectrum, B mode power spectrum that's generated from from the E-mode power spectrum. And since that's purely sourced by lensing, we're going to be able to get a better measurement of the CMB lensing through measuring polarization, but at the same time measurement of the damping tail in polarization itself. Okay, so at Pol, we're very excited because we had first light last month. It's much faster than ACT was and has polarization sensitivity with thousands of detectors. The temperature sensitivity should be increased by about 4 times, as well as measuring polarization. And we're going to be conducting both wide and deep surveys on the sky, covering deep patches of 100 square degrees, and also thousands of square degrees on a wider patch. We're going to be observing the sky on the equator, which has a huge amount of overlap with other wavelength data too, so that you can cross-correlate the lensing signal with optical and other wavelength data too. This is just an image of the cryostat here before it was put into ACT. The science we're after, again, it's two things. The first is to get the E-mode damping tail. And the science we want to do with that, the kind of things I've been talking about already, probing the recombination physics. But then the second thing is the lensing. By the fact that the E-modes are lensed into B-modes, by measuring the polarization, we have much better measurement of the lensing signal. And one of the most exciting things I think we can hope to do is constrain the sum of neutrino masses. With ACT Pol, we should be getting into the sum of neutrino mass limits less than 0.2 EV regime. The forecasted limits, 1 sigma limits, are 0.07 EV for ACT Pol combined with Planck. So we can hope to quite soon get under that interesting regime where we can, for example, rule out or at least disfavor quasi-degenerate models where you've got quite a large minimum neutrino mass. And that's a number that, with ACT Pol, we hope to do excitingly well, but there are even going to be a next generation of instruments that can do even better with CMB lensing. We'll also be looking to probe curvature and dark energy. In particular, if there's anything strange going on at redshift 2 or 3, CMB lensing is a really unique measurement constraint on that. This just illustrates a simulation done by Blake Sherwin of a deep ACT Pol field where this would actually be the recovered lensing power spectrum on a small patch of the sky, where that is going to be signal dominated. Those fluctuations will be the actual lensing fluctuations showing you the dark matter field on the sky. So that's coming soon. My final thing, I just want to advertise a new result that I've had nothing to do with, but I think is very cool, which is the first detection of B-mode lensing from SPT Pol. It's been on the sky for the last year or so. This was put out in a paper by Duncan Hansen and the SPT team just recently. What they've measured is, this is a map of the E-mode polarization mapped by SPT Pol. This is then a measurement of the lensing field actually reconstructed from the Herschel satellite. And using that, you can predict what the B-mode polarization map should be given an E-mode CMB map and a lensing map. And that's shown over here. And they then cross-correlated this predicted lensing map with their detected B-mode signal and found they were highly correlated and thus made a detection of the B-mode angular power spectrum in lensing. And that's shown here. So this is the power spectrum against angular scale. And these are detections of the B-mode. So it's what we expect to see, but it's a really neat first result. There's also polar bear experiment, which is taking data too. So we've got these 3 experiments measuring the CMB lensing. And we should soon see more exciting results from them. Okay, just to summarize, at small scales, the CMB is probing both recombination and CMB lensing. The temperature spectrum's now been measured by ACT, SPT, and Planck to LF 3000. I've shown that there's excellent consistency between the spectrum and the results we've got from ACT and WMAP versus from Planck. CMB lensing really is fast growing. And it's a field that's going to be, you're going to just see many, many more results from in the next few years. In addition, we're going to get polarization measurements of the small-scale CMB. And we've seen this neat first detection of B modes from SPT Pol. Cross correlations with other probes are going to be something that's going to be also done more and more. And there are really exciting prospects for neutrino physics. Thanks.
Okay, thanks very much. Are there any questions? David Lyth, can you get the... There we go.
Oh, just a comment about the running of the spectral index. You mentioned minus 0.001 as the prediction of inflation.
I know that's not. That's very simple.
That's only if the inflaton perturbation generates the curvature perturbation, and only in the simplest models.
That's right. I'm sorry. I should have clarified that. That's absolutely right. Yeah.
I mean, if it were some other field like the curvaton, say, then I would say the central value is 0, but with a very wide spread, it could be anything really.
Yeah. No. Thanks for making that point. I think we should still try and measure it though.
Mm-hmm. Any other questions? Mark?
With polarization measurements, do you have the predicted sensitivity to go for BB, and in particular cosmic string BB?
Yeah, so I don't have that forecasted number off the top of my head, but we will be getting a measurement. So we'll be measuring the B mode spectrum with the ground-based. So there's two kind of regimes of angular scales. There's a whole lot of very large-scale experiments that we're going to hear about from John. And some of those will be useful for the cosmic string BB measurements. With ACT-Pol, we're going to be going small scale, and so we can look there as well. But we'd be limited probably to L of a few hundred and greater with ACT-Pol due to our angular coverage. So I don't have the forecast off the top of my head, but yeah, I think we're going to do better, and I should figure out what the number is.
Okay, there's a question right up the back. Maybe this will be the last one. Yeah, right. Over there. Sorry. Thanks. John, could you start to set up if that's right?
I have a question about cosmic strings that you mentioned.
Yeah.
Naively, one would think because cosmic strings tends to add small-scale power to the total power,
Yeah.
that if you allow for it, the spectral index for the adiabatic modes would be driven redder, not bluer, which seems opposite of what you mentioned in the talk. I wonder, can you explain?
Well, let's see. So let's see. Yeah, the spectrum used to be tipped up steeper with additional cosmic strings. Let's just think. I can see, yeah, if you just add small-scale power, I can see that you would want to compensate for that with a smaller spectral index. But I think that was also coming so I wasn't quite, because I was showing an L to the 4 plot. If I showed a L squared plot, there's actually a strong peak. It goes up and then down, right? So it's actually the up. It's the up that used to do it, and now it's the fact that you've also got small-scale power that's also constraining it. So it's that peak that's changing it. It's not just a straight increasing.
Okay, well, we better finish there. Let's thank our speaker again.